Hello everyone, welcome to Basic Electronics Tutorials. In this video, I'm going to take up the second numerical on bridge rectifier. Let me read out the question first. In a full wave bridge rectifier, the transformer secondary voltage is 200 sin omega t. The forward resistance of each diode is 30 ohms and the load resistance is 1 kilo ohms. Calculate Part A of the question, DC output voltage, Part B, ripple factor, Part C, efficiency of rectification, and Part D, peak inverse voltage across non-conducting diode. Let us start with the solution now. As I said, the voltage across the transformer secondary is 200 sin omega t. This, please note, is in the form of Vm sin omega t, where Vm is the maximum voltage across the transformer secondary. So with that, we established that the maximum secondary transformer voltage is 200 volt. Further, we are also given that the load resistance RL is 1 kilo ohm and the diode forward resistance is 30 ohm. Okay, let us start with part A of the numerical now, which is to find the DC output voltage. The DC output voltage is denoted as VDC and is given by VDC equals IDC multiplied by RL. Let me call this as equation 1, where IDC is the average or DC output current. Since IDC is not known, let us write the equation for IDC, and this is given by IDC equals 2 divided by pi Im. This is a standard equation for the full bridge rectifier, and let me call this as equation 2. Im in equation 2 represents the maximum secondary transformer current, and it is given by the formula Im equals the maximum secondary voltage, which is Vm, divided by the resistances in the circuit. Now generally we write the equation for resistances as the forward resistance of the diode plus the load resistance. But please note, this is a bridge rectifier, and in a bridge rectifier, during both the positive as well as the negative half cycles of the input supply, two diodes will be conducting. So when I write the forward resistance for the diode, I should write it as 2Rf, indicating two diodes will be conducting either in the positive or in the negative half cycle. Then we have the load resistance RL. Let me call this as equation 3. Now in equation 3, we have Vm, which we previously calculated, and is equal to 200 volt. The value of Rf is given. The value of RL is also given. So let us start substituting and find the value of Im. So this is equal to Vm, which is 200, divided by 2 multiplied by Rf, which is 30, plus RL is 1000 ohms. So the answer for Im is 0.1886 amperes. Once I find Im, I will substitute that into equation 2 to find IDC. I am going to rewrite the equation 2 here. IDC equals 2 divided by pi into Im, which is equal to 2 divided by pi multiplied by 0.1886. So this is equal to 0.120 amperes. And lastly, once I find IDC, I'll substitute that back into equation 1 to find the DC output voltage. I'm going to rewrite equation 1 here. VDC is equals to IDC multiplied by RL. IDC is 0.120. RL is 1000 ohms. So the answer for DC output voltage is 120 volt. This is the answer for part A of the numerical. The part B of the numerical is to find the ripple factor. This is once again a very easy question because the ripple factor for a full bridge rectifier is 0.4836 and is a constant. However, I will demonstrate how this value is obtained using mathematical analysis. The equation for ripple factor is given by square root of IRMS divided by IDC whole square minus 1. Let me call this as equation 4, where IRMS is the value of RMS secondary transformer current and is given by Im divided by root 2, where Im is the maximum value of transformer secondary current, and we have computed it previously and is equal to 0.1886 amperes. So, dividing it by root 2 will give us the answer for IRMS as 0.1333 amperes. We have previously computed IDC, which is 0.120. So, let us now substitute all these values back into equation 4 and compute ripple factor. IRMS is 0.1333, IDC is 0.120 whole square minus 1. Solving this, you will get 0.4836. This is a fixed value for a bridge rectifier. In the examination, if I ask this question, you can directly write 0.4836 is the ripple factor for a full bridge rectifier. Well, that is the answer for part B of the question. Let us now move on to part C of the question, which is to find rectification efficiency. It is generally denoted by eta and is given by PDC divided by PAC, where PDC is the DC output power and is given by VDC multiplied by IDC. We have previously computed both of these values. VDC is 120 volt, IDC is 0.120 amperes. So, the value of PDC is 14.4 watts. Next, PAC. PAC is the AC input power and is given by VRMS multiplied by IRMS. Please note, we have not computed VRMS. However, it is not a problem because I will represent VRMS in terms of IRMS, and it is given as IRMS multiplied by the resistances in the circuit, which is 2RF plus RL. So, the final equation for this is IRMS square multiplied by 2RF plus RL. Let us substitute. IRMS is 0.1333. We have a square. Then we have 2 multiplied by RF is 30 and RL is 1000. Computing this, you will obtain the answer as 18.835 watts. Once we have computed PDC and PAC, we can now substitute it back into equation 5, which is for the rectification efficiency as eta equals PDC divided by PAC. Now, this is efficiency, so I will modify the equation by multiplying it with 100. PDC here is 14.4, PAC is 18.835, then we have 100 multiplied. So, the answer for this is 76.45%. This is the rectification efficiency. This is the answer for part C of the numerical. Coming back to the last part, we are asked to find the peak inverse voltage across the non-conducting diode. This is again a very straightforward answer. The answer for this is simply Vm, the secondary transformer maximum voltage. So, I will write the peak inverse voltage across the non-conducting diode is equal to Vm, which is equal to 200 volt. That is the answer for part 4 of the numerical. Well, with that, we have come to the end of this video. If you like this video, kindly like and share this video and subscribe to my channel for more tutorials on basic electronics. Thank you for watching. Have a good day.